Many people ask us about the difference between ionic minerals like are found naturally in the Great Salt Lake that MRI produces and makes available, and colloidal minerals that many of our competitors make available in their products. One of the important difference by definition is that ionic minerals have a charge. Ionic minerals by definition are minerals that have been completely separated, and because they have been separated, they have either a positive or negative charge, and the body uses that charge to pull nutrients into the villi of the intestine, into the bloodstream, and the body uses that charge in every aspect of metabolism to pull in nutrients and expel waste. So charge is very important. In comparison, somebody may have a similar label claim, but if the elements don't have a charge, they won't have the same potential for absorption and benefit within the human body. Another very important aspect of ionic minerals that I want to emphasize today is size. Textbooks tell us that, for example, the size of an ion of magnesium is 1 × 10⁻⁶ microns. Okay, that's very small. That's so small that you can't see that. In comparison, by definition, colloids are a conglomerate or a molecule that's small enough to be in suspension in a liquid. By definition, that molecule is about 1 micron. Okay? Compare 1 micron of the colloids with 1 × 10⁻⁶ microns of, that would be the size of, for example, a magnesium ion. To illustrate that a little bit better, on this piece of paper, I have a ball bearing that is exactly 1 millimeter. If we say that this little teeny ball bearing on that paper is a model or represents an ion of magnesium, and if we wanted to make a similar model or a model to the same scale to represent a colloid, how big would that colloid model have to be? This ball bearing has a radius of 1 millimeter, so a colloid to the same scale would have to have a radius of 1 kilometer or 0.6 of a mile. That's huge. That's not even really even on the same scale. What that means also, if you had a sphere with a radius of 1 kilometer, inside that sphere you could fit 1 quintillion of these 1 millimeter ball bearings that represents the ion. Most people aren't familiar with the term quintillion, so I'll tell you, that's 1 × 10⁸, or 1 with 18 zeros. Said yet another way, that's 1 billion billion of these 1 millimeter models would fit in a ball, in a sphere with a radius of 1 kilometer. That means that if the body were to ingest a colloid, the body would first have to break down 1 quintillion molecular bonds before that colloid would have the same potential for absorption as the ionic minerals as they are found naturally provided by nature in the waters of the Great Salt Lake. Another interesting thing is that if you look at a bottle of many of the competitors, you'll notice sediments on the bottom. If there's sediments on the bottom, that actually means that those minerals aren't even true colloids. They're minerals that were temporarily in suspension, but unless they're permanently in suspension, they can't even be considered a true colloid. And if you can see small particles in the liquid, in order to see the small particles, they have to be at least 40 microns. So that even magnifies the difference or the potential benefit that you'll find in colloidal minerals and what's naturally found in the brine of the Great Salt Lake, even that much more. In conclusion, I would just like to say that when it comes to mineral absorption, size does matter and charge is very important.